All right, so we've talked a little bit about functions of several variables from section 1. We're going to skip section 4.2, which talks about limits in the context of functions of several variables and continuity in those contexts. It's not that those aren't interesting subjects, it's just that spending the time on that section I don't think is worth sort of prioritizing. So we may revisit some of those things a little bit later in the semester, but I'll just talk about those topics when we get there. Which takes us to chapter or section 4.3, where we talk about partial derivatives. So now we're returning back to calculus in the context of functions of several variables. Partial derivatives are a way of doing differential calculus one variable at a time using what you've already learned in Calculus 1 about the derivative. The goals here are to, of course, be able to calculate partial derivatives, and you're going to find that it's relatively straightforward because many of the formulas that you learned in Calc 1 are still relevant here. And to determine higher order partial derivatives, and there's something interesting there that happens. For example, I can take the partial derivative with respect to x, and then the partial derivative of that with respect to y, and get mixed partial derivatives. So that's an interesting sort of new feature. And then, of course, we want to understand the meaning of partial derivatives, and so we'll spend some time thinking about that. So how do partial derivatives work? Essentially what you're doing is taking this function of several variables, a function of say x and y, you're holding all of the independent variables fixed and differentiating in the remaining variable. So if I want to take the partial derivative of f with respect to x, I pretend that y is a constant and I just differentiate with respect to x in the ways that I learned in Calc 1. What do partial derivatives tell us? They tell us lots about how the function is changing with respect to a single variable. What they don't tell us is how the function changes in combination in combinations of those variables. But what we'll see later is we can actually tease out even that information if we know all of the partial derivatives. We can figure out how a function is changing with respect to a collection of independent variables. That collection of partial derivatives is something that we'll call the gradient in this case, and that's what we would call the derivative of a function of several variables. If you're looking for one thing to hang your hat on and say that's the derivative of the function, it's called the gradient. We'll talk about that in a couple of sections. Right now, we're just focused on partial derivatives, and partial because we're only looking at rates of change in a single variable as opposed to all of the variables simultaneously. And of course, higher order partial derivatives correspond to taking the second derivative or the third derivative in a particular independent variable. One really curious thing about mixed partial derivatives, as I mentioned, you could take the derivative, the second order partial derivative, you could say partial with respect to x, and then take the derivative with respect to y. What's interesting about this is there's a theorem that says that it doesn't matter which order I do that. I could take the partial with respect to x followed by the partial with respect to y, and the result will be the same if I take the partial with respect to y and then take the partial with respect to x. This remarkable result is called Clairaut's theorem, and it's very useful in theory, and I find it somewhat surprising. A lot of the geometric ideas about derivatives from Calc 1 and Calc 2 carry over into Calc 3. For example, the partial of a function with respect to x tells us the slope of a surface in the x direction. The partial with respect to y tells us the slope of the surface in the y direction. Concavity similarly. The second derivative, the second partial of a function with respect to x tells us the concavity of the surface or of the trace in the x direction. Similarly, the second derivative with respect to y tells us the concavity of the trace in the y direction. Mixed partials also have geometric interpretations, but we're not going to really focus on them. They're a little bit subtler and not super relevant to many of the things that we'll explore later in the semester. All right, let's do a bit of a flyover of the section and then we'll get to the examples. So let's focus first on functions of two variables, although I don't make as much of a distinction between functions of two variables, functions of three variables, as the book likes to do. When in doubt about a derivative, if I want to take the partial derivative of a function with respect to x, go back to the definition of the derivative and write a difference quotient. If I want to take the partial of f with respect to x, pretend that x is an independent variable and that y is a constant. And then just do what you did in Calc 1. Take the difference quotient in the x variable and keep the y variable constant. Take the limit as h goes to 0, and this is the definition of the partial of f with respect to x. This is the notation that we use. We also use this notation over here, where we have f sub x, and that's the same as the partial of f with respect to x. That's the same as taking this limiting process. Similarly, if we want to find the partial derivative of f with respect to y, we hold x fixed, we just treat it like a constant, and we do the difference quotient in the y variable, just like that. Notation is similar, partial of f with respect to y, f sub y. We don't get to use the prime notation anymore because prime is ambiguous when you have several variables. Which variable are you differentiating with respect to? So we have this new notation that abandons the prime notation and uses either this fraction notation, partial of f with respect to x, or this subscript notation, f sub x, the partial of f with respect to x. So the notation's different, but the derivatives are relatively the same. For example, let's pretend we have this function of two variables, x and y, and we want to take the partial of f with respect to x. We could go ahead and do this difference quotient process, and we would end up with 2x minus 3y minus 4. And I want you to be able to do that on simple examples, but I also want you to be able to use the tools of Calc 1 to compute these derivatives. And if we look closely at this, we can just go through term by term. Take the derivative of this term with respect to x. That's 2x. The derivative of this term with respect to x, don't worry about the y, pretend it's a constant. Hence the derivative with respect to x is negative 3y. The derivative of this term with respect to x is 0. If we treat y as a constant, there's no x component to it, so the derivative of constant with respect to x is 0. Derivative of this with respect to x is negative 4. Of this with respect to x, 0. Of this with respect to x, 0. So you already have these skills at your disposal because of Calc 1. Practice a little bit with the difference quotients, but we'll mostly be relying on the formulas and tools that we learned in Calc 1. Let me just do this one right here because I want to remind everybody about how the chain rule works. So in the second one, we're asked to calculate the derivative with respect to x of sine of this expression. So you take the derivative of the sine, you get cosine of the expression, and then you use the chain rule. And again, nothing super special is going on here. It's just when you apply the chain rule, you take the partial derivative with respect to x of what's inside, and that turns out to be just multiplying by 2xy minus 2, and then the 4 goes away. It's 0. So again, all of the usual rules from Calc 1 apply. You're just holding the other variables constant. What does this mean geometrically? Well, if you are taking, say, the partial derivative of this function of two variables, which we can recognize as a surface, the partial with respect to x is giving me the slope at this point in the x direction, or parallel to the x direction. And the partial with respect to y is giving me the slope of the surface in the direction parallel to y. That's just two of many possible directions. What if I want to know the slope of the surface in this direction that's not parallel to either x or y? Well, we have a tool for that. It's called the directional derivative, and we'll learn about that a little bit later. For now, the partial with respect to x is just telling me about the slope in the x direction. Partial with respect to y, just telling me about the slope in the y direction. There is this really fun relationship between partial derivatives and contour maps. Let's remind ourselves of this old example where we have this function g is the square root of 9 minus x squared minus y squared. You may remember from the previous section that this surface is actually the upper half of the sphere of radius 3. All right, well, if we look at the level curves of this thing, we get sort of the expected behavior. The level curve for c equals 2 is a circle. That's the horizontal cross-section of the upper hemisphere. Horizontal cross-section of the upper hemisphere. And if we drop down closer to the xy plane and take a horizontal cross-section, at say c equals 1, we get a slightly bigger circle. And if we go all the way down to the xy plane, that's z equals 0, the level curve corresponding to 0, we get actually the circumference of that upper hemisphere as it sits on the xy plane. We get a circle of radius 3. So all of this kind of makes sense, and these are evenly spaced level curves, 2, 1, 0. We could actually look at the level curve for c equals 3 as well, and what we would get is a single point here at the origin. There's only one point that satisfies g equals 3, and that is the point x equals 0, y equals 0. Gives me the square root of 9, which is equal to 3. So evenly spaced level curves would have a point here for c equals 3, this circle for c equals 2, c equals 1, c equals 0. All right. Imagine that you're sitting here and you travel in this direction in the domain of the function. Remember, the domain of g lies in the xy plane, and in this particular case, the domain of g is the interior of the circle of radius 3. It's everything inside and on this blue curve. So if I'm in the domain, let's say I'm in the domain and I'm sitting here at the point 3, 0, and I move towards the origin, what's going to happen to the values of the function g as I do that? Well, if I move from here to here, the value of the function went from 0 up to 1. In other words, it increased. And if I move from the orange to the turquoise line, the value of the function went from 1 to 2, also increasing. And if I go from 2 to the origin, where this is the level curve corresponding to c equals 3, again, it went from the value 2 to 3, so it increased. That makes sense because if you imagine the dome of this hemisphere and you're starting over here and traveling in the domain towards the origin, what are you doing on the surface? You're rising up steeply at first and then less steeply at the top. If we think about the partial derivative of this function g with respect to x as we move in this direction, right? As x decreases, the function increases. What do we know about the slope in that situation? That slope is negative. So we would expect the partial derivative of this function with respect to x, that is in the x direction, we would expect it to be negative here. Put another way, if I start here and I move in this direction, the values of the function are decreasing as x increases. So we would expect the partial derivative of g with respect to x at this point to be negative. Over here on the other side, what would we expect the partial derivative of g with respect to x be here as we move towards the origin? It's increasing. We would expect the partial with respect to x to be positive here. Let's repeat this thought experiment for the partial of g with respect to y. Let's say down here, as we move towards the origin, the function wants to go from 2 up to 3, right? So we would expect the partial as y increases, we would expect the partial of g with respect to y at this point to be positive. When we get up to the peak, it's going to be 0, and as we go down the other side, we would expect the partial of g with respect to y on this side of the domain to be negative. It's a little subtler if you're not on these axes in this particular example, but I think we can argue that if I'm sitting here and I move in the direction parallel to the y-axis, that I'm going to be climbing up the dome of the hemisphere until I get here, and then I'll start to fall down the other side. So in fact, the partial of g with respect to y in this area is positive, and the partial of g with respect to y in this area is negative. Here, because as we move in the increasing y direction, we're going up the surface, and here as we move in the increasing y direction, we're going down the surface. So there is this interesting relationship between partial derivatives and their signs, SIGN, and the slopes of the surfaces parallel to the coordinate axes. For functions of more than two variables, I'm not going to belabor the point. The difference quotients are the same. It's just that we get a third coordinate here. And if we had functions of 5 or 10 variables, you can imagine what those difference quotients would look like. You'd start to run out of letters, but you can imagine what they'd look like. Calculating partial derivatives for functions of 3 variables, same deal. Hold 2 of the variables fixed and differentiate in that third variable to find the partial derivatives. Use all of the rules that you learned in Calc 1 for this. For higher order partial derivatives, it's exactly the same. If I want to take, say, 2 derivatives in the x direction, I take the partial with respect to x of f, and then I just do it again with respect to x. If I want to take the second partial of f with respect to y, I take the first partial, and then I just do it again with respect to y. Interestingly, there are mixed partial derivatives where I can first take the derivative with respect to y here, and then with respect to x, or I can take the derivative with respect to x and then with respect to y. So there are actually 4 second derivatives for a function of 2 variables, and there are even more for a function of 3 variables. I'll let you figure out how many. And of course, there are even more when we get to the third derivative, right? fxxx, fxxy, fxyy, fyxx, and so on. And again, it's an exercise in combinatorics to actually count them. Calculating second partial derivatives, same thing. Just hold these variables fixed and apply the rules as you learn them in Calc 1. We'll do a few examples at the end. A really startling result is that it doesn't matter the order in which you do mixed partial derivatives. I can differentiate with respect to x and then with respect to y, or with respect to y and then with respect to x, and the results will be the same. It's good practice for you to verify that that's what happens, good practice in differentiation. Now, for this particular section and this particular book, we're not interested in partial differential equations. Not that that isn't a fantastically useful area of study, but if you want to study partial differential equations, take engineering math with me next semester. That's where we study partial differential equations. We're going to completely ignore them in this class, and you can safely ignore the exercises at the end of this section that involve partial differential equations. So we can stop right here. With that, let's jump over to the examples down to the bottom here. And in fact, I've already cut and pasted these examples into our notes. So I'm going to jump over to the notes and wrap up here with a few examples. All right, in this first exercise, we want to compute the partial derivative using the definition only. So here we're asked to find the partial of z with respect to x using the definition. So let's write the difference quotient definition for the partial of z with respect to x. That's the limit as h goes to 0 of the function. I'm going to call this, just for the sake of keeping track of things, I'm going to call this thing f of x and y. F of x plus h comma y minus f of x y over h. And now let's fill in all the bits. So we have the limit as h goes to 0. And let me add a little bit more space in here. Limit as h goes to 0. Okay, now we need to substitute x plus h in everywhere we see an x. So we have x plus h quantity squared minus 3 times x plus h times y plus y squared. Good. That's the f of x plus h part of things minus the quantity, just f of xy. So that's x squared minus 3xy plus y squared, just like that. All over h, the parameter that's going to 0. Great. All right, let's see here. We can simplify a few things. For example, right off the bat, we see that that is going to go away. But the rest of it's going to require a little bit of work. So we'll start expanding things out and hoping that we get some nice cancellation. Why do we need cancellation? Well, at the moment, we can't just let h go to 0 because if we send h to 0, we're essentially going to get 0 over 0, indeterminate form, not sure what's going to happen. So remember, when you're doing these derivative problems using the definition, the goal is to do a little bit of algebra so that you can cancel this problematic h in the bottom that wants to go to 0. Well, if your function is differentiable, you should be able to do that. Let's expand out x plus h squared. That's x squared plus 2xh plus h squared minus 3 times x times y minus 3 times h times y. We already got rid of the y squared, but we have a minus x squared. We have a plus 3xy. And of course, the second y squared is also gone. Let's see if some nice cancellation happens here. We do have an x squared and an x squared going away. We do have a 3xy and a 3xy going away. That's convenient. Now, we don't have any more cancellation, but the beautiful thing is everything that's left has a factor of h in it. Let me put that 0 in there. So let me clean up this mess and you'll see that. We'll take this factor of h out, and what's left behind is 2x plus h minus 3y. All of that's over h. And if I've done the algebra correctly, this cancels. And as h goes to 0, this goes to 0. And we get 2x minus 3y. So using the definition of the derivative, we end up with the partial of z with respect to x being 2x minus 3y. Does that look correct? Well, if you go up here and look at the original equation and do the derivative holding y fixed and taking the derivative with respect to x, we get 2x, good, minus 3y, good, plus 0. So it all checks out. All right, so taking the derivative using the definition, the partial derivative using the definition, agrees with taking the derivative just using the techniques of Calculus 1. Now what I'd like to do is connect the partial derivative to the geometric features of the surface. So in this case, we're asked to calculate the sine of the partial derivative using the graph of the surface. So we want the sine of the partial derivative at the location. So here we're talking about the partial of f with respect to x at the point 1, 1. So let's find the point 1, 1, and we'll do this by sketching a line that's kind of parallel to the y-axis and a line that's kind of parallel to the x-axis, and we see where they intersect in the domain below the surface. It's very hard to kind of see where that is without being able to rotate the surface, but this is a bowl shaped surface, and I think the intention is that the minimum of the bowl, the bottom of the bowl, is at the origin. Everything else is uniformly up and away from the xy plane. So we find the point 1, 1 one along the x-axis, one along the y-axis, and the place where they intersect is right there, and we go up to the surface. And we ask ourselves, what's the partial of f with respect to x? It indicates the slope of the surface as we travel in the direction of increasing x, so that's this direction, and I'm on the surface. What's happening to the surface? Well, it certainly appears that the surface is going up as I move in this direction parallel to the x-axis. So that would suggest that the partial of f with respect to x is going to be positive here, greater than 0. Let's try one more and I'll let you figure out these remaining two. So let's do 115. So now we're asked to look at the partial of f with respect to x, not at 1, 1, but in fact at minus 1, 1. So that point is going to be back here somewhere, and it's even harder to see, but maybe sort of right here on the surface or in the domain, however you want to imagine it. And of course, these lines here are along constant y, and we can see that in the direction of increasing x, the surface appears to be dropping at this point. So we would expect this partial derivative to be less than 0 at that point. So it's positive over here at the point 1, 1, and it's negative over here. This is just one direction. I want you to think about, for example, in 116, you're asked about the other direction, the y direction at the point 1, 1. All right. And I've got a couple of exercises like this in the web work too, and you should definitely work on that. The geometry of partial derivatives is very important to understand. Here's a little bit harder partial derivative problem where you're asked to invoke the chain rule. Still a function of two variables. We want to take the partial of z with respect to x and then with respect to y. Partial of z with respect to x is just the function, the derivative of hyperbolic sine of h, which you may remember is the hyperbolic cosine. And then 2x plus 3y. And then by the chain rule, the derivative of what's inside with respect to x. The derivative of what's inside with respect to x is just 2, and we clean that up, and we get the hyperbolic cosine of 2x plus 3y. The partial of z with respect to y, I'll let you work it out, but it's going to be hyperbolic cosine of 2x plus 3y. The only difference is when you take the partial derivative of what's inside, invoking the chain rule, you get a 3 because we're differentiating with respect to y instead of x. Make sense? All right. So those are the first partial derivatives. You might practice this by doing second partial derivatives. All right, and we're really upping the ante here. We're doing a third derivative, partial of f with respect to x, followed by the partial with respect to y, followed by the partial with respect to z. So this is going to be a bit of work. We'll start with the partial of f with respect to x. We go through each term. We hold the y and z variables constant. We get 3x squared y z squared. Those are constant. Again, in the next term, we take the derivative with respect to x. That's 4x y z. The y and z just go along for the ride. In the third term, partial with respect to x, 3z. And in the last term, there is no x, so we can just leave it out. The derivative is 0. Now we want to take, in order to find fxyz, we need to find fx followed by fxy. So we now differentiate fx with respect to y. Let's do this again. Differentiating the first term with respect to y, which appears right here, we get 3x squared z squared. The second term with respect to y, 4x z. And the third term with respect to y, there's no y, so we get a 0. And we're almost there, fxy z. We now take the derivative of fxy with respect to z. In the first term, we get 3 times x squared times 2z, which nets out to 6z, or 6x squared z. And in the second term, we have a lone z sitting there, so the partial of that term with respect to z is just 4x. We can check this in Sage, and I'm doing this mostly so that you can see a way of doing complicated partial derivatives using Sage. Sage is more than capable of doing these kinds of partial derivative calculations. So let's jump over to Sage and create a Sage worksheet for this. And let's create a new worksheet, and let's name it after the exercise. This is exercise 144, and we want to create a new Sage worksheet. Now remember, independent variables have to be declared in some sense in Sage, so we let Sage know that, hey, we've got these 3 independent variables that we're going to be playing around with, just letting you know. If you don't do this, Sage will not understand what's happening. We talked a little bit about assumptions last time, and if you want, you can put assumptions on these variables. For example, we can assume that x is real, assume that y is real, and finally that z is real. This is not super important for the particular exercise that we're working on, but if we're doing more complicated partial differentiation and we start asking Sage to simplify things and there are trig functions involved or exponentials or logs, these assumptions will help. So it's always kind of good to get in the practice, even though this particular exercise doesn't require it. Let's put our function f in there as we were given in the textbook. So, or maybe not in the textbook, but in the exercise. So I'm going to type this whole expression into Sage as f. So that's x cubed times y times z squared minus 2 times x squared times y times z plus 3 times x times z minus 2 times y cubed times z. And it's always good to proofread these things. So again, x cubed y z squared minus 2x squared yz plus 3xz minus 2y cubed z. That looks good. And you might even ask Sage to show you f in its nicest way, just to again convince yourself that things are what they should be. Now the fun part, we can let Sage do all the differentiation at once. Diff, there's going to be 3 derivatives, and remember the diff command is how we invoke differentiation in Sage. So we have a diff of a diff of a diff. What's the first derivative going to be with respect to? X, followed by a derivative with respect to y, followed by a derivative with respect to z. And again, if you want to see this neatly typeset, we could surround the whole command with a show command, and that will take the output and take it from this sort of crude ASCII representation to a nice representation. And what we see is 6x squared z minus 4x. Let's go back to our notes. 6x squared z minus 4x. They totally agree. So our hand calculation is verified by the Sage calculation. Look, we don't always have to do this, but if you have really complicated expressions and you're punching it into WebWork and WebWork's saying, nope, that's not right, you might just go through Sage and use it to check some of your intermediate calculations. Just to maybe help you find an error. And usually if you're making an error in this kind of stuff, there's some kind of basic misconception about how the differentiation is working. So it's really important to have a tool like Sage or Wolfram Alpha help you kind of break down the steps and help you identify where there might be mistakes lurking. Okay, the last exercise of the section foreshadows something that we'll be doing a little bit later. Um, Remember back in Calc 1 when we were maximizing and minimizing functions, we were taking derivatives and setting them equal to 0? Well, guess what? Taking partial derivatives and setting them equal to 0 has meaning also. And we're not going to talk about that meaning today. We'll talk about it in another section. But the task of taking a partial derivative, setting it equal to 0, that's something that we want to begin thinking about and practicing right now. So what you're asked to do in problem 146 is to take the partial with respect to x, with respect to y, set them equal to 0, and solve the resulting system of equations. What you're going to get is two equations in the two unknowns, x and y. And if you're lucky, you'll be able to solve that system of equations, and you'll be able to find important points that we call critical points in Calculus 3, just like in Calculus 1. So the first thing we need to do is calculate the partial derivatives. The partial of f sub x, the partial of f with respect to x, is 4x plus 2y. That's 0. That's 2. That's 0. The partial of f with respect to y, the first term is 0, the second term is 2y, the third term is 2y, and the last term is 0. And these are the two partial derivatives that we're going to use to answer this other part of the problem. We're going to set them equal to 0. And what we have are two linear equations in the unknowns x and y. I'm going to label those equations 1 and 2. And if you look carefully, if we subtract 1 from 2, we're going to get rid of the y's. We're going to eliminate the y variable. So let's do that. Oops, I have a typo here. That should be 2x. So let's do that. We'll subtract 2 from 1. Sorry, 2 from 1, not 1 from 2. So we'll look at 1 minus 2. And what we get is the equation 2x. The two y's cancel, and we get a 2 going along for the ride. And the right-hand side of the equation, 0 minus 0 is just 0. If we solve this equation for x, we find that x is equal to negative 1. If we take that and substitute into equation 2, we quickly see that y is equal to 1. And there's a single solution, one solution to this system of equations, and it is the point negative 1, 1. Something special happens on this surface at the point negative 1, 1. We've answered the question. We're done, right? We've answered the question. There it is. But let's go quickly over to GeoGebra and have a look at this surface and see if we can't figure out what's actually happening at the point negative 1, 1 in the domain. So we'll go over and invoke GeoGebra, and we'll pull up the 3D calculator. And let's plot this function of two variables and see what the surface looks like. We're talking about 2x squared plus 2xy plus y squared plus 2x minus 3 equals z. All right. And what's emerged here is some kind of possibly an elliptic paraboloid. We can actually reduce the scale, I guess increase the scale depending on how you want to talk about it, along the z-axis. And what we see is it looks like it's just a paraboloid, an elliptic paraboloid. And it's got a point down here. It has sort of a minimum point somewhere. I'm going to also plot the point negative 1 comma 1, negative 1, 1, 0. I'm plotting that point in the xy plane. And it's not an accident that it happens right at the center of this ellipse. What do you think's happening at that point in the domain? Well, of all of the points in the domain that I could plug into this function, it looks like plugging in -1, 1 is going to make this function attain its lowest point. And we could actually plug that into the function to figure out what that lowest value is. We could plug in x equals -1 and y equals 1, and what we would learn, so what is the value of f at this point? Well, let's plug in -1 and 1. We get 2 plus -2 plus 1 plus -2 minus 3. Let's simplify that a little bit. So we have, what, -5 here and +1, -4. So we should see that minimum occurring just about -4. And it does look like that might be right at -4 on the z-axis. So that makes sense. And in fact, we can test that if we change the z-coordinate here to -4. I said -4, not 4. Let's put a minus sign in there. Yep, and now we see that point is sitting right at the minimum of this function. So what this is hinting at is that this process gives us a way of finding maximums and minimums on surfaces, a generalization of the ideas that you've learned in Calc 1 about maximizing and minimizing functions. All right, just to wrap up here, again, I want you to go through the suggested or the exercises at the end of the section, but you can stop at problem 149 and ignore everything after that because that's all related to partial differential equations. It's all stuff that I want to de-emphasize in this particular class. Once you've got you've done enough of those exercises to kind of get a grip on the topics, jump over to WebWork and do the assessment for section 3, chapter 4. Thanks a lot.